Welcome back to Xul Podcast, Shooting the Reality. I'm James Caro.
And I'm Emily Lora.
And we're here for another deep dive.
Yeah.
You chose a really fascinating topic for us this time.
The origin of the universe.
The origin of the universe.
Yeah.
We've got a whole stack of sources here, articles, infographics, even a YouTube video all ready to unpack. Right. We're talking about the Big Bang, of course.
Of course.
But also some of those wilder theories out there.
Right.
How everything might have begun.
Exactly. Should we start with the reigning champ then? The Big Bang. It is the most widely accepted model, after all.
Makes sense to me.
Yeah.
But you know how I'm already curious about those alternative theories.
Yeah.
We'll get to those later. Right?
Absolutely. We'll explore those too. But first, let's ground ourselves with the basics.
Hmm.
Imagine, if you will, the entire universe squeezed into a space smaller than an atom.
Okay.
It's incredibly hot dense. And then, bam! It explodes, kicking off the expansion of space and time. That's the Big Bang in a nutshell.
Wow. Talk about starting with a bang.
Mm-hmm.
But how do we actually know that this happened? It's not like we had telescopes back then.
Good point. But we have evidence. And it all started with Edwin Hubble's observations back in the 1920s. He noticed that galaxies are moving away from each other.
Oh,
And the farther away they are, the faster they're receding. It's like dots on an expanding balloon.
that makes sense. So everything's moving apart, which
Right.
means it all must have been together at some point.
Precisely. Now, the American Museum of Natural History has this really clear timeline of what happened after the Big Bang,
Okay.
which took place about 13.8 billion years ago.
Wow.
The early universe was like a superheated soup of mostly hydrogen and helium gas. And as this gas cooled over billions of years, gravity started to pull it together, forming the first stars and galaxies.
So from this chaotic soup, order began to emerge. That's pretty amazing.
It really is. And here's something that I find absolutely mind-blowing. Everything we see around us, the Earth, the sun, even our own bodies, is made from the remnants of those early stars. We are literally made of stardust.
That's incredible. I never thought of it that way before.
Yeah.
It makes you realize how connected we really are to the universe.
Exactly. It puts things into perspective, doesn't it?
It really does.
But there's a twist. The initial Big Bang theory, as elegant as it is, ran into a couple of problems, things that didn't quite add up.
Yeah, okay. What kind of problem?
Well-
Did somebody spill the cosmic soup?
Well, not quite. These problems are known as the horizon problem and the flatness problem.
Okay.
Let's start with the horizon problem. Imagine the universe just after the Big Bang.
Okay.
Even though everything started from a single point, the most distant parts of the universe, which wouldn't have had time to interact with each other,
Right.
somehow have almost the same temperature.
Ah,
It's like making soup and having every spoonful at the exact same temperature without ever stirring it.
yeah. That doesn't sound right. How do we explain this?
Exactly. And that leads us to the flatness problem. We observe that the universe is remarkably flat, but any slight deviation from perfect flatness in the early universe should have been amplified over time by the force of gravity, leading to a very curved universe. It's a bit like placing a marble on a perfectly flat surface. Any tiny imperfection will cause the marble to roll away.
So according to these problems, we should be living in a lumpy, unevenly heated universe.
Yeah.
But we're not.
Precisely. Those discrepancies led to the development of a new idea, cosmic inflation.
Cosmic inflation. Tell me more.
Well, imagine that a fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion.
Okay.
We're talking faster than the speed of light expansion.
What?
This is cosmic inflation, and it's like hitting the fast-forward button on the expansion of the universe.
Okay, so this rapid expansion,
Mm-hmm.
how does that solve the problems we talked about?
Let's start with the horizon problem. Cosmic inflation suggests that those distant parts of the universe were actually in close contact before inflation occurred,
Okay.
giving them time to reach the same temperature. So our soup analogy works again because everything was properly mixed at the beginning.
Okay, that makes sense.
Yeah.
So how does it address the flatness problem?
Think about blowing up a balloon. As it expands, any initial wrinkles or bumps get stretched out, making the surface appear smoother and flatter. Cosmic inflation did the same thing to the universe. It stretched out any initial curvature. So what we observe now appears incredibly flat, even though it might not have been perfectly flat at the very beginning.
That's a pretty neat explanation. So this cosmic inflation smoothed everything out.
Yeah.
But what actually caused this rapid expansion?
That's where things get even more interesting. The leading idea is that quantum fluctuations, those tiny random energy fluctuations that happen at the subatomic level, might have been responsible for kicking off inflation.
Interesting.
And here's the mind-blowing part. Those tiny fluctuations were then stretched out by inflation to become the seeds for the large-scale structures we see in the universe today, like galaxies and clusters of galaxies.
Wow, so those tiny quantum jitters were blown up to become galaxies.
Exactly.
That's just, wow. So the Big Bang, combined with this concept of cosmic inflation, helps to explain a lot about the universe we see today.
Right.
But I know there are other theories out there too.
Yes. While the Big Bang is the most widely accepted model, it's not the only one.
Okay.
There are alternative theories that offer different perspectives on the universe's origins.
Now we're talking. I'm really curious about those alternative theories.
I thought you might be. But first, let's take a closer look at a couple of the main problems with the initial Big Bang theory. These problems actually led to some pretty wild alternative theories.
Okay.
One early rival to the Big Bang was the steady state theory. It proposed that the universe has always existed, and matter is continuously created throughout space to maintain a constant density as the universe expands.
No beginning, no end. Just eternal existence. It was a compelling idea for a while.
It was, but there were some holes in it.
Like what?
Well, if matter is constantly being created, wouldn't that mean the universe is getting more and more crowded?
That's a great question.
The steady-state theory proposed that matter is created at a very slow rate, so slow that it would be virtually undetectable. But over time, evidence supporting the Big Bang, particularly the discovery of the cosmic microwave background radiation, led to the steady-state theory falling out of favor.
So the Big Bang won that round. What are some of the other contenders?
Well, one that's particularly mind-boggling is the eternal inflation theory. Remember how we talked about cosmic inflation happening for a brief period right after the Big Bang?
Right.
Well, eternal inflation suggests that inflation never actually stopped.
Wait, so it's still going on, but how is that possible?
The idea is that inflation is happening in this incredibly high-energy state, and it's constantly expanding.
Okay.
But within this expanding space, little pockets can transition to a lower energy state, kind of like bubbles forming in boiling water.
Okay, I'm picturing these bubbles. So what are they?
Each bubble could be a separate universe, potentially, with its own unique set of physical laws and constants.
Really?
Meanwhile, the inflating space keeps expanding, creating more and more of these bubble universes, a multiverse.
So you're saying there could be a universe out there where gravity works differently, or where the speed of light is slower?
It's a possibility, and here's another thought. If there are an infinite number of these universes, then every possible combination of physical laws and constants would exist somewhere.
Whoa, so there could be a universe where I'm a rock star, or where donuts grow on trees.
Uh-huh. Well, maybe. But it's important to remember that this is all highly speculative. The multiverse, if it exists, is beyond our ability to observe directly. It's a consequence of some of the current models, but still very much in the realm of theory.
Okay, I'll try to keep my expectations for donut trees in check. But are there any other alternative theories that try to explain what came before the Big Bang or what might have caused it?
There are. Another interesting one is the oscillating model, which suggests that the universe goes through endless cycles of expansion and contraction.
Endless cycles.
It's kind of like a cosmic heartbeat. Our universe expands for billions of years, eventually reaching a maximum size, and then it starts to contract, pulling everything back together in a big crunch.
A big crunch.
This crunch then leads to another Big Bang, and the cycle starts all over again.
So no beginning, no end. Just this eternal cycle of expansion and contraction.
Yeah.
But doesn't that run into some of the same problems as the Big Bang, like the issue of everything starting from a singularity?
You're right to point that out. The singularity problem is definitely a challenge for the oscillating model, just as it is for the Big Bang. And that's where some of the more recent theories, particularly those rooted in string theory, try to offer some different perspectives.
Okay, string theory. That's the one that talks about tiny vibrating strings being the fundamental building blocks of the universe, right?
Exactly. String theory attempts to unify all the forces of nature, including gravity, which is notoriously difficult to incorporate into other theories. And it's within the framework of string theory that we find some really intriguing ideas about the origin of the universe.
So how does string theory explain the origin of the universe? Does it have its own bang moment?
Well, it gets a little complex, but one of the ideas that comes from string theory is the concept of asymptotic past triviality. It basically suggests that in the infinite past, the universe was in an incredibly simple state, empty, flat, and devoid of any interactions.
So even simpler than that super hot, dense state before the Big Bang.
Yes. But here's the catch. Even in this simple state, gravitational instability would inevitably lead to the formation of black holes.
Black holes, the cosmic vacuum cleaners.
Yeah.
So how does this relate to the Big Bang?
Well, instead of the universe emerging from a singularity, some string theorists propose that our universe might have actually sprung forth from the interior of a large black hole.
Wait, so the Big Bang was really more of a bounce out of a black hole. That's wild. But how would a black hole even give birth to a whole universe? It's not like things can escape from a black hole, right?
That's where things get even more mind-bending. We usually think of black holes as these inescapable cosmic traps. But in the context of string theory, the extreme conditions inside a black hole might lead to a bounce, a point where the intense gravity and density cause a reversal, leading to an expansion, a Big Bang.
Okay, so the matter collapsing into a black hole somehow gets turned around and explodes outward, creating a universe.
Exactly. And this scenario avoids the problem of a singularity because the universe doesn't start from an infinitely small point. It emerges from a pre-existing state, the interior of a black hole. It's all very theoretical, of course, but it offers a fascinating alternative to the traditional Big Bang singularity.
Okay, I'm starting to see how string theory can shake things up. But if this is true, wouldn't there be some evidence of this black hole bounce?
There might be. One prediction is a specific pattern in the cosmic microwave background radiation, the leftover heat from the Big Bang. This pattern would be like a fingerprint left behind by the black hole's collapse and subsequent expansion.
So scientists are actually looking for this pattern.
They are, and future telescopes with their increased sensitivity might be able to detect it. That would be a huge discovery, providing evidence to support this string theory-based explanation of the Big Bang.
That's incredible. I'm already excited about the future cosmology.
Me too. There's so much we still don't know, but the quest to understand the origins of the universe is one of the most exciting and intellectually stimulating endeavors in all of science.
Okay, so we've talked about the Big Bang and some pretty amazing alternative theories, but we're just scratching the surface here, right? Are there other cosmic mysteries we need to explore?
Absolutely. We'll delve further into the implications of these theories, and I'll tell you about a mind-blowing concept called scale factor duality symmetry, which suggests there might have been a pre-Big Bang phase that mirrors our own universe.
Hold on a second. So you're saying there might have been something before the Big Bang?
It is, but it's also what makes cosmology so fascinating.
You were about to tell us about something called scale factor duality symmetry.
Right.
What exactly is that, and what does it have to do with the Big Bang?
It's a fascinating idea that comes from string theory. Think of it like looking in a mirror. Scale factor duality suggests that what happened before the Big Bang is like a mirrored reflection of what happened after. So just like we had inflation expanding the universe after the Big Bang,
Okay.
there might have been a similar expansion happening before the Bang.
Whoa, a mirror image universe before our own. So there could have been another universe contracting before ours started expanding. That's pretty wild.
It is a pretty mind-blowing concept. And one of the predictions of this idea is that there should be a detectable signal in the form of gravitational waves.
Gravitational waves.
Specifically, we would expect to see a blue spectrum for these waves, meaning their intensity increases with frequency.
So not just echoes of the Big Bang, but echoes from this pre-Big Bang era. But wouldn't those signals be incredibly faint by now?
They would be. But the hope is that future telescopes, like the proposed LISA mission, will be sensitive enough to detect them. It would be a groundbreaking discovery, providing evidence to support this mirrored universe idea.
That would be incredible. Finding evidence of a pre-Big Bang universe would completely change our understanding of cosmology. But you mentioned that there are some challenges with this idea, right?
There are. One of the main challenges is that the predicted blue spectrum of scalar perturbations, these are the tiny density fluctuations that eventually led to the formation of galaxies and large-scale structures. Right.
Clashes with observations of the cosmic microwave background radiation.
Oh.
Those observations show a nearly flat spectrum, which means the intensity of those fluctuations is roughly the same across different scales.
So a conflict between theory and observation, that seems to happen a lot in cosmology. Does that mean this string theory explanation is a dead end?
Not necessarily. There are ways to reconcile the theory with observations. One idea involves a mechanism called the curvaton mechanism, which introduces another field besides the inflaton field that drives inflation.
Okay.
This additional field, called the curvaton, can generate a flat spectrum of density perturbations during the post-Big Bang phase, smoothing out the wrinkles, so to speak, even if the inflaton's fluctuations have a blue spectrum.
So the curvaton acts like a cosmic iron, smoothing out those density fluctuations. But how does this connect back to the pre-Big Bang phase and scale factor duality?
Well, if scale factor duality holds true, then there should have been a similar smoothing mechanism at play during the pre-Big Bang phase as well.
So even though the initial fluctuations might have had a blue spectrum, this other field, perhaps a string theory axion, could have flattened them out before the bounce leading to the nearly flat spectrum we observe in the cosmic microwave background radiation.
It's like a cosmic game of telephone. The message gets passed along, but it's modified along the way. So are scientists looking for evidence of this curvaton field?
They are. It's a very active area of research. Finding evidence of the curvaton or any other field that could have played a similar role would be a major step towards understanding how the universe could have emerged from a pre-Big Bang phase.
This has been an incredible journey, Emily. We've gone from the Big Bang to the multiverse and explored some truly mind-bending ideas from string theory.
It has been quite a journey.
It's amazing to think that we've come so far in our understanding of the cosmos, yet there's still so much more to discover.
It is remarkable how far we've come, and it's a testament to the power of human curiosity and our desire to understand the universe and our place within it.
Well said. Well, Emily, thank you so much for taking us on this deep dive into the origin of the universe.
It was my pleasure. Always a pleasure to talk about cosmology.
And to our listeners, if you enjoyed this deep dive, be sure to subscribe to Xul Podcast and leave us a comment. We love hearing from you. Until next time, keep shooting the reality.